graphing logarithms. So I'm going to ask us to construct a graph of 3 different logarithms first. All of these are called parent functions. A parent function, this is a good example of one right here, is always one that we can kind of use as our baseline function. And then we can do transformations to that type of function, like moving it left or right, moving it up or down, stretching it vertically, stretching it horizontally, reflecting it over an axis. So the parent functions are kind of what we start with. So this is the parent function log base 2 of x. Here's another parent function down here, log base 3 of x. And then we do all of our transformations to that function. The base is kind of the part that's the parent function part of it. We've seen other ones like y equals x as a parent function, y equals x squared as a parent function for quadratics. That's what I mean when I say parent functions. What we're going to do today is we're going to graph, and we're going to start by saying we want 2 values for x that are fractions. There's a couple ways we can do this. Like I've assigned x values here, and one of the ways I like to think about this is if I take this function y equals log base 2 of x, and I want to change forms or find the inverse, rewrite it, I can say 2 to the y equals x. And this is kind of like what we did on the homework, where you'd say, well, 2 to the y equals, let's start with like the second one, we'll say 1/2. I think that might be an easier one to see than 1/4. But we have to ask, what does y have to equal in order to turn 2 into 1/2? And it would have to be -1, because when you take a negative, you're going to really flip it over and make it 1/2 to the first power. So the y value has to be -1 if x equals 1/2. It's almost like we're working backwards here. We're trying to figure out what's the y value to get to that x value. And then if I did 2 to the -2, I would hopefully get 1/4, because first -1 makes it 1/2, and then 1/2 squared, once I do the -1, that's going to make it 1 squared is 1, 2 squared is 4. So this becomes a -2. And I can just kind of keep working through those types of problems where I just got this form of the equation, 2 to the y power equals x in exponential form. And I'm just trying to figure out what does y equal. So 2 to the y equals 1. That's the next one. And it has to be a 0, because anything to the 0 power equals 1. And then the next one, 2 to the y equals 2, because the x value was 2. I'd have to say, oh, well, it has to be the first power. 2 to the first power equals 2. So that's going to be a 1. Okay. And we just kind of work through the problems like that. And when we get to this one here, this is kind of an interesting one. 3, this is the one I really want to focus on here. Y equals log base 2 of 3. If I were to rewrite that form, I would get 2 to the y equals 3. And I know 2 to the first equals 2, and 2 squared equals 4. So 3 is going to be some type of decimal answer. And honestly, I want to try and avoid decimal answers for my y values. If I'm good, I can avoid those decimal answers and work right around them. Because, for example, like I said, 2 squared is 4, so I can make this a 2 right here. And I can choose x values accordingly. So, for example, thinking about my y values here, they want -2, -1, 0, 1, 2. If I just kept going with y values, 3, 4, 5, 6, for example, what are the corresponding x values going to be? So, like if I did 2 to the third, where 3 is the y value, 2 to the third equals 8. So the x value would be 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. And hopefully we start to see that pattern. Hey, this is like the numbers are doubling each time. 4, 8, 16, 32. We might remember back in the day, AGS1, where we're seeing this like, hey, times 2, times 2, times 2. All right, that goes all the way back to your AGS1 roots right there. Except this time it's the x value that's multiplying by 2 instead of the y value, because it's the inverse of the original exponential equations that you would have dealt with back in AGS1 and the start of AGS2 as well. All right, so we're just seeing that again. Now, time to graph it. I can take these x values I found, 1/4 comma -2. That's going to be somewhere right there. 1/2, that's halfway between 0 and 1, comma -1. 1 comma 0, 2 comma 1. I'm going to skip the 3 one because that was a decimal. 4 comma 2, 8 comma 3, 16 comma 4. And unfortunately, my graph doesn't scale much past that. So I can go ahead and sketch my graph through those points. It'll be a nice smooth curve. And then I'll leave the paper. And then I put arrows on it to show it goes on forever. The point 32 comma 5 is going to be over there somewhere. I just don't have room for it on this graph that was given to me. And I asked you specifically to include 2 fractions because I want you to realize that there is actually a vertical asymptote here at the line x equals 0 that we can't cross. We're never going to be able to get an x value that's negative, because if I just kept working backwards with my y values, like, hey, let's try y is -3, then I'm going to get 1/8. Let's try y is -4, I'm going to get 1/16. Y is -5, I'm going to get 1/32. I'll get numbers closer and closer to 0, but I'll never actually get to 0 because there's a vertical asymptote there, which makes sense because the inverse equation was 2 to the x equals y. If I did that inverse, well, I'll just keep it in terms of y is actually 2 to the y equals x. When I do this equation, it doesn't matter what I plug in for y, I'm never going to get a negative number for that x output. So the domain here happens to be, it's going to be 0 to positive infinity. We can see the x value is going to the right to infinity. But 0 is not included in the domain. I cannot get a 0 for an x value. And then the range of any logarithmic function is -infinity to infinity. And we talked about domain of an exponential function is -infinity to positive infinity, and then the range happens to be where that horizontal asymptote is. And then because of inverses, the domain and range swap. So the domain of an exponential is -infinity to positive infinity. The range of its inverse, a logarithmic equation, is -infinity to positive infinity. Okay, so that's the idea for this first graph here. Now, when we're graphing these functions, we could do something very similar on part B here, where I say, let's do y equals log base 3 of x. So we can rewrite that as 3 to the y equals x. And honestly, what might be the easiest thing to do for these types of problems is to assign y values first. Like, hey, let's do y as -2, -1, 0, 1, 2, 3, and 4. We'll just do those for our values. And say, what happens when you get 3 to the -2 power? 3 to the -1 power, 3 to the 0 power, 3 to the first power, 3 squared, 3 cubed, 3 to the 4th. We're plugging in all those values for y. This is a lot easier, in my opinion, to solve than dealing with that dang logarithm. But hopefully we'll pick up another pattern here. 3 to the -1st, for example, is 1/3. What's 3 squared when I do 3 times 3?
9.
9. So I've got 3 to the -1st is 1/3. 3 squared is 9. So 3 to the -2nd would be 1/9. 3 to the 0 power, anything to the 0 power is just 1. 3 to the first power is 3. 3 cubed is 27. 3 to the 4th is 81. So I get 1/9, 1/3, 1, 3, 9, 27, 81. And just like that, I've got my next table done. And hopefully we see another pattern. This time the x values are times 3, times 3, times 3, times 3. All because of this 3 down here. Now when I plot these ones, 1/9 comma -2, it's going to be super close to the axes there, but not quite touching. 1/3 is also going to be pretty close. 1 comma 0, 3 comma 1, excuse me, 9 comma 2, and then 27 comma 3 is actually off our paper already. So when I sketch this line, I want to sketch it out and off the paper before I get to the line y equals 3. Really important to note, because I don't want you to do this, like something like that, because that's assuming that there's a point of like 11.5 comma 3, which we know there's not. It's 27 comma 3. So just make sure you're drawing an accurate picture when you draw these things. So I'm just drawing it off the grid before I hit the line y equals 3 there. Just that's what I mean when I say an accurate picture. There's going to be another vertical asymptote here, same exact spot, x equals 0. Parent function is going to have the same asymptote. So the domain is 0 to infinity, range of any logarithmic function, -infinity to +infinity. All right, and that's what this looks like. If I were to graph this on a calculator on Desmos, it might give me an error message, or it might look really weird. So you just have to know that the range is -infinity to +infinity, because the calculator won't always give you that correct range. Okay, so that's what problem B looks like. Problem A, we saw log base 2, and we were able to see the x values go times 2, times 2, times 2. Problem B, we saw log base 3, and we're able to see the values go times 3, times 3, times 3 for the x values. So problem 4, we see log base 4. I want you guys to go ahead and fill out the table for problem 4, and then sketch the graph and identify the domain and range. So take a minute to do that, and I'll fill it in just a second here. So now when we talk about translations, what happens when we move the graph left or right? What happens when we move the graph up or down? How does that impact the function overall? So that's kind of where we're moving towards next. And like every other time we've done graphing, I have the expectations for what we should get done on our graphs. So today it's going to be find at least 6 points to fill the table. And then 2, the input values should be fractions. That's 2 of the x values need to be fractions. All right, and the reason I want fractions for the x values is because that's going to be kind of determining where your vertical asymptote is. Because as we shift the function left or right, that vertical asymptote is going to move off of x equals 0. It might be x equals 1, or x equals -1, x equals -3, something like that. So we just have to be careful about that. Draw the axes and set an appropriate scale for the function. State the domain and range for the function. All right, those are the 4 things we want to do. So on this particular problem, first let's just talk about finding the inverse of it, like rewriting the form. This one's not too bad because we have a logarithm on one side and we have the y equals on the other. So what we would do is we would start by saying 2 to the y power equals x plus 3. And that's how you get rid of that logarithm. We'll talk more about solving logarithms later, but this is just in general, we're doing that same process. And then to get x by itself, we're going to need to subtract 3 from both sides. And now we have x by itself. So what's really happening here is we're going to start with assigning a y value like we did before. And then we plug that in here. And then we're going to subtract 3 from that result. And that'll be our x value. So what I mean by that is, let's start with the y values. Let's just do the same ones we did before. -2, -1, 0, 1, 2, 3, 4. Let's start with an easy one. Like let's say 2 to the 0 power. Well, 2 to the 0 power, that's this part right here, corresponds to this line here. What we're doing is we're We're working backwards, so we're doing the opposite of the logarithm. We're going to say, let's do this 2 to the y power. 2 to the 0 power happens to be 1. So that 1 becomes a 1. And then 1 minus 3 is negative 2. From here, we're subtracting 3 from each of the values. And then that means our x value is going to be negative 2. So if we plugged in negative 2 for the x value, we would get 1 for the y value. And that actually does make sense, because if you look at this, you're going to get log base 2 of 1. And we talked about how log base anything of 1 is always going to equal 0. And that's why the y value equals 0 there. So just thinking about it logically from the logarithm side, it makes sense. If it makes more sense to you just to stick to exponents, that's perfectly fine. And we kind of do this for all of them. Like, let's go to 2 to the negative 2 now. We already know 2 to the negative 2 is going to be 1/4. And that's kind of where this column comes in here. That should be a 1/4. Then that should be a 1/2. That should be a 1, a 2, a 4, an 8, and a 16. You might recognize that this column happens to be the exact same as the column from the parent function log base 2 of x. And then we just take all of those numbers and we subtract 3 from them. 2 minus 3 is negative 1. 4 minus 3 is 1. 8 minus 3 is 5. 16 minus 3 is 13. 1/2 minus 3, that's kind of a tricky one. We could rewrite 3 as 6 halves. So 1/2 minus 6 halves is negative 5 halves. And then 1/4 minus 3, we can rewrite 3 as 12/4. 1/4 minus 12/4 is negative 11/4. And then we have negative 1, 1, 5, 13. Just copying those columns down. That's how we come up with our x and y columns for this function, kind of working backwards. Okay, doing the opposite of what we'd expect to do. Now this time though, I want to point out before we do any graphing, we have negative numbers for x for the first time. So it is possible to have negative numbers, but there's a limit to what they can be. And that actually happens inside the parentheses here. We can tell a domain of a logarithmic function by looking inside the parentheses. The domain used to be x equals 0. And now because we're saying plus 3 inside the parentheses, what's the new domain, do you think?
Negative 3.
Why negative 3? Why not positive 3?
Because the x values are stretching back into the negatives.
Exactly. The x values are stretching into the negative. So great answer saying negative 3 and not positive 3. Because what happens is when we kind of look at it backwards, we're taking all of our x values and we are subtracting 3 from them right here, minus 3. So you do the opposite of what's in the parentheses. That's really the trickiest part with trying to identify these domains. So what's really happening then, our domain becomes negative 3 instead. Basically, you're taking all of the x values and you're subtracting 3 from them. So 0 minus 3 is negative 3. Infinity minus 3 is still infinity. So that's why you just can't really change infinity. And the range of any logarithmic function is still going to be negative infinity to positive infinity. So now when I create my axes here, I'll go ahead and create an xy axis right there. And I'll draw, draw one in the middle here. And we'll say this is x, this is y. And we'll count the y's by ones. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. We'll count the x's by 2's. Negative 4, and we'll go 4, 8, 12, 16, 20. And now I know there's going to be an asymptote at x equals -3. If you can identify it from the equation, that's awesome. If you can see, hey, there's a parentheses here, and the asymptote's going to be the opposite sign of whatever's in that parentheses, good on you. That's what I want you to be able to recognize off the top of your head. And now I can plot the line. I have -11/4, which is essentially very close to -3, comma, -2. And then I have -5/2, comma, -1. And then I have -2, comma, 0, -1, comma, 1. And then I have 1, comma, 2. So that's going to be over here. And then I have 5, comma, 3. And 13, comma, 4. And then it would just kind of go off the paper from there. So if I did a scale of 1 for the x's instead of 2, I wouldn't have been able to include that last point, 13, comma, 4. But, I mean, it's not a huge deal if I missed that 1 point. I think I still would have had 6 points there. I would just do another fraction point if I needed to get my 6 points. But that's the idea for sketching these ones. Find that vertical asymptote. That's going to help you establish your domain and range. And then you can sketch all the values. Okay. Problem number 2, unfortunately, is where it's going to get a little bit trickier. And the reason problem 2 gets a little trickier is because now it's this 3 plus, and that's not attached to the logarithm. So what you need to do first is you need to subtract 3 from both sides of the equation. So you go y minus 3 equals log base 2 of x. So I'm going to make a note over here. We're going to talk again. We're going to talk about this more with solving, but in order to change forms, you must first isolate the logarithm. All right, you have to isolate the logarithm. What I mean by that is get log base whatever on one side by itself. And that's what we've done here by subtracting 3 from both sides. Now it's just y minus 3 equals log base 2. And then we can change forms. 2 to the y minus 3 power equals x. That whole y minus 3, which is on the other side of the equation, that is the exponent. The exponent is y minus 3. So now, that's what we're going to do on this line here. Is the first thing we're going to do is whatever we put in for our y values, we're going to say we're going to subtract 3 from them. And then, once we subtract 3, we'll do the 2 to the y, and that'll end up with our x value here. So this is where it can get a little trickier because let's say I start with -2 for y. And I do 2 to the -2 power minus 3 equals x. That ends up giving me 2 to the -5th power, which is going to give me a really tiny fraction, which is possible. I can take care of that. It would just give me a -5 over here because I'm subtracting 3 from it. And then 2 to the -5th, well, I know 2 to the 5th is 32. So 2 to the -5th would just be 1 over 32. And like I said, it would give me a very tiny fraction to work with there. So I could start with the -2 and work my way down from those. Or I could be smart and say, I want this column right here to be those -2's again. Well, there we go. I want this column right here to be the -2, the -1, the 0. And instead, I'm going to work forwards and add 3 to all of the y values. It's kind of a weird way to think about it, but it's possible. It's a possibility to do that. Because now I can say this is 1, this is 2, this is 3. 1, 2, 3, 4. And this is 4, 5, 6, 7. So that's a possibility to do it as well. And what that does is that means this column matches up right here with my y values from above. And then all I'm doing from there is just undoing that. 1/4, 1/2, 1, and then 2, 4, 8, 16. So it can make the rest of the problem a little bit easier if I can recognize that part. If I want to start with my -2's over here and subtract 3 and do -5, -4, -3, you're more than welcome to do that. It's entirely whatever you feel comfortable with. But I'm just trying to show you a shortcut way to kind of think about this. Okay, trying to identify which of those columns can I line up as best I can to my advantage to save myself some work. Now this one is going to have, this problem should have the y-axis being our asymptote at x equals 0. And then when I plot the points, I should be able to hopefully plot all of them here. So without much of a problem. Okay, so when I plot these points, I could just scale by 1s this time, and that would exclude my last value of 16, but that's perfectly fine, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm still going to have 6 points on my graph here. I'm going to do 1/4, comma, -2. Or I'm sorry, it's going to be 1/4, comma 1. 1/2, comma 2. 1, comma 3. 2, comma 4. 8, comma 5. Or sorry, it was 2, comma 4. 4, comma 5. And then 8, comma 6. And then the last point, like I said, 16, comma 7 would not fall on the graph, but I do have 6 points plotted already, so I think I'm okay with that. And then I can go ahead and sketch this off the paper. And there's my my second sketch there. Domain, again, because of where the asymptote is. This time, the +3 affected the y values. It moved the whole function up 3 units. And then the range is still -infinity to +infinity. Okay, so now I've got 2 problems I want you guys to try with these translations. See if you can identify the domain and range. See if you can sketch a graph and create your own table. And if you don't want to use those middle parts, if those are too tough, that's perfectly fine. If you want to just try and work with the outside parts, the x's and the y's, that's perfectly fine. Whatever works best for you guys. All right, so take a few minutes to work on those 2 graphs now. Let me know if you have any questions at all. But that's what problems 3 and 4 look like. And the last thing I wanted to bring up was just the transformations that are taking place. So it says given that function y equals a plus log of x, that a value, that represents a vertical translation. So you're either moving the function up or down. It only affects the output values. You put the x in, you do the logarithm of it, and then you're just saying add or subtract this a value. That's the vertical translation. And then the other part, the b value, that represents the horizontal shift or the horizontal translation. This also moves the asymptote. So the value inside the parentheses is really important because that's the one that's going to impact what happens to the asymptote. Notice that the asymptotes for these last two questions, one of them was x minus 2. We do the opposite. So the asymptote's x equals positive 2. The other one was x minus 1 in the parentheses. Do the opposite. X equals positive 1 is your asymptote. That's the idea for these types of problems.